Hello everybody, I'm Gleb and today I'm going to tell everything about latency in 5G networks. Let's get started. Please note, this information is only for general purposes. Please use your own official manuals, guidelines and technical specifications from your vendor. Today I'm going to start with definitions. What is latency? What is round trip time? What's the difference between of them? Then we will move to end-to-end budget. What kind of things, nodes can contribute to overall latency? Then I will tell you about every possible aspects of radio access network and how some features and capabilities of radio access network could impact on latency, including TDD patterns, subcarrier spacing, how exactly resource allocation and handovers could impact on latency. Then we will talk about transport layer, what kind of things here could impact on latency as well. Then we will consider possible scenarios for latency testing and the difference between them. Then we will evaluate possible impact on end user experience and what kind of things could be used for that. Of course, we will talk about possible requirements for different use cases and a little bit talk about security and latency, what kind of things here. The thing is that latency was always a KPI for network. It was always a metric which impacted on user experience from GSM networks through 3G, 4G networks, and in 5G, latency becomes more and more important because it opens new possibilities for new services. And that's why we should know every possible aspect and what to do with latency actually. There are so many terms: latency, jitter, round trip time, processing time. So let's understand what's the difference between of them. Let's start with latency terminology. According to Wikipedia, latency in packet switch networks, this is one-way measurement of time from the source sending a packet to the destination receiving it. Now let's look at 3GPP definition. Latency, the time from when the source sent the packet to when the destination receive it. Again, sounds very easy, yes, but we know that in reality, latency depends on throughput, on system capacity, by other words. Of course, size of information also has impact. We should start with the fact that latency is a kind of a cumulative metric. This is a sum of transmission delay, propagation delay, time which information spent in queue, plus some time for processing that messages. There are a lot of things that contribute in overall latency. There are some opinions that ping measurements could be used for accurate latency measurement. In many cases, it is not suitable, and we will talk about it as well. So again, latency is a huge topic, and the main goal of my presentation to you is to make a little bit order in our communication society. So let's continue with round trip time. Again, according to Wikipedia, round trip time is a length of time it takes for signal to be sent plus the time for acknowledgement of that signal to be received. For that definition, this is two-way round trip time. This is a two-way time of unloaded path. So there is no any packets in any buffers. What we can say now, we can define that latency, usually latency, it is a one-way. Round trip time is a two-way of latencies. And first of all, we should say that round trip time do not equal 2 times of latency, because in downlink direction and in uplink direction, latency, any delays could vary a lot. And usually, actually, in mobile networks, uplink latency is much higher than in downlink. So that's why round trip time and just double latency, that's a big difference. Now let's talk about ping time. According to Wikipedia, round trip time could be measured as a ping time, but I think this should be not true in reality, because ping time depends on a lot of things as well. For example, ping packets could not trigger high data rates by their nature, whereas round trip time is derived directly from the TCP logs and any data post-processing tools. Ping request and ping reply messages transported over ICMP protocol, whereas this is different from usual user behavior. Also, ping time depends on latency itself, depends on time for initial connection setup. Also, ping time depends a lot of amount of data, period of inactivity. Now let's look at minimum round trip time. Minimum round trip time, actually this is a part of round trip time plus time which could be spent in queue because of some capacity limitations obviously, and some variations. Basically we may call it as a jitter. Minimum round trip time depends a lot of network infrastructure, especially when we're talking about transport and core network. Time in queue depends on system capacity, link capacity basically, number of nodes. What kind of nodes this could be. In ideal network, queuing time should be 0, but in reality we know it could have some time. And variations for mobile networks mainly because of bad radio conditions or bad conditions in other links, in optical links, in microwave links as well, but mainly because of radio conditions. So when it comes to variability of round trip time, we can say that this is a jitter. And jitter actually depends on UE movements, depends on changes in radio conditions, nodes overload, but mainly changes in radio conditions in real networks. So we may call also it as a kind of a reliability metric. So in order to define strict requirements for latency, that's obvious, it is better to define some kind of a range for latency, and in that range time of round trip time could vary. So because we are working with real networks with changes in node loads, in radio conditions, so but anyway we should avoid at all costs latency spikes. This is when latency unstable. So stability in this case is required for real-time services. Also, it is important to mention that latency do not equal time to connect. Yes, it is all about time metrics, but time to connect is mainly determined by instant throughput. So here is throughput is much more important than latency of our network. So that's why there is a big difference between 1 megabit per second and 15 megabit per second for time to connect. And there is almost no difference between 10 millisecond latency and 80 millisecond of latency for that impact of time to connect. Now let's look at overall end-to-end latency budget. If we look at the left side, we can see user with certain requirements for user experience. That user may use some user equipment with certain capabilities, with certain operational system software, with application, and all of that things could contribute in overall latency. Then of course goes 5G air interface or any other air interface basically. Then it goes air interface with all changes in radio conditions. Then we have base stations with certain architecture, standalone or non-standalone, and that base stations with certain run features could impact on latency drastically as well. Then we have transport network with lots of different nodes, switches, routers, and itself it has architecture which could also impact on latency. Then we have core network with again some nodes with certain capabilities for computing, for processing information. Then it could be some firewalls or border gateways, security gateways, for they could spend some time of end-to-end latency for for example, for any inspection of packets. So they can contribute, again, they can influence on it. And of course, we have internet and server. So that part is usually out of mobile operator responsibilities. We hardly ever could influence on that. Probably we could manage end server. For example, we could locate end server at the edge of base station and realize as a kind of a solution for mobile edge computing. And that's why we can reduce end-to-end latency. We will talk about it as well. So let's start with end user capabilities and how it could impact on latency. So we know that UE could have different capabilities. It depends on the release, it depends on some feature support, number and location of antennas, especially for millimeter waves, some limitations related to different chip makers. Of course, there is a software, there is an operational system, and how exactly software aligned with hardware, it is also extremely important. Of course, there is some application installed. It could be speed test, it could be browser, or it could be a very complex and processing and time-consuming AR, VR application, which could introduce some latency for displayed for render information, which could also contribute in overall latency, and we should take it into account. And of course, there is just let's say non-objective factors, because for different use cases, different requirements is needed. For example, if we're talking about human communications, communications between people, it would be one requirement. If we're talking about industrial robots, probably appropriate tactic in latency should be choose as well. So that part is also has very important to overall latency. When it comes to air interface, in any wireless networks, signal to noise ratio, or basically signal quality, it is a key to low air interface latencies. That's the fundamental thing, that high interference, it leads to low signal to noise ratio. Low signal to noise ratio results in low probability of receiving and demodulating information, and a low probability for error corrections, which is insanely used in any wireless system, including 5G, of course. A low probability for error correction leads to high probability of retransmissions, and retransmissions, it is what we want to avoid at any cost. So low signal to noise ratio lead to high retransmissions. And high retransmissions, it is all about latency. It is all about contribution to latency. So good coverage, it is a key for low latency for any networks. Now let's talk about what kind of things from radio access network point of view could impact on latency. In 5G networks, we know that there are multiple subcarrier spacings. In LTE, it was 15 kilohertz subcarrier spacing and certain slot duration and symbol duration. In 5G, there are a lot of things, and usually we can choose high subcarrier spacing. It is available. So if we look at this table from 3GPP specification, we can see that just by physics, actually, the high subcarrier spacing, the shorter slot and one OFDM symbol duration. And we know that scheduling, it operates in time domain mainly. So the how fast scheduling, how fast resource allocation works, it depends mainly on duration of OFDM symbol or slot duration. So that's why high subcarrier spacing is more appropriate, is more a better way for air interface latency. But we should understand that choosing high subcarrier spacing will inevitably lead to shorter serving area, because not only useful information shrinks in time, but also guard time, or we can say cyclic prefix is also becomes shorter, and it leads to more inter-symbol interference. So that's why our serving area for such cases should be very limited in order to be able to provide low latency. And of course, usually hardware is more complex if that hardware could work with high subcarrier spacing. That's why we should understand possible positive and negative impacts of certain band for latency operation. And that's obviously that using lower bands could give us relatively good latency abilities. Let's say it could also give wide area coverage, but very limited to capacity. So that's why sub 1 gigahertz is mainly for voice services, is mainly for some not so heavy content, for Internet of Things devices. Whereas if we look at millimeter waves, usually this is a story about local area cases. With millimeter waves, we can choose certain patterns for TDD network, and we could choose high subcarrier spacing, which very good in terms of extreme capacity, extreme low latency, but again, coverage is also extremely limited. And if we're talking about any mid bands, any C band or sub 6 gigahertz, there is also possible to achieve pretty good low latency, especially with some radio access features. But our coverage is more or less moderate, and our capacity is also high. So I think that bands in sub bands. So I think sub 6 gigahertz is also very suitable for many latency applications. When it comes to TDD patterns and latency, we should understand that here the main contributor is uplink downlink switching. So that's why we should choose appropriate TDD patterns, for example 4x4 or 8x2. Of course, it depends on the load in uplink and downlink direction. It also depends on abilities, hardware and software which is available for your network. But basically, we should understand that FDD networks are more suitable for low latency operations because there is no any restrictions in time domain. But at the same time, FDD networks are not so present in millimeter waves. Basically, they not so present in 5G, and most of current and future 5G networks will be with TDD. So that's why choosing appropriate TDD pattern for your case is crucial. We know that in 5G networks also it is possible to operate with mini slots, or by another way, symbol-based scheduling is also possible. You can allocate 2, 4, or 7 of them symbols, and that symbols actually not exactly should be started with slot boundary. Whereas in previous 4G networks, there is a strict 1 TTI, which is equal 1 millisecond. So so we can conclude that there is a kind of a focus for low latency operation, which was initially designed in NR specifications. And symbol level scheduling together with subcarrier spacing could provide low latency with support of relatively good throughput. There is also an opinion that mini slots shorter than 7 symbols should not be considered for TDD operation because overall overhead of switching between uplink and downlink slots would become significant and too short for slot lengths. In 5G networks, there is also a possibility for resource allocation type B. It means that there is a start from any symbol within a slot. And if we look at my example here, we can see from the left side PDCCH area with dedicated information then some guard period when there is no transmission, and then goes DMRS signals for demodulation purposes. They always goes before the main PUSH transmission, and then goes short format of PUCCH for acknowledge, not acknowledge, and other system information. So that kind of flexible slot configuration is also very good for latency purposes, but the negative aspect, of course, is that very good NR coverage is required, because downlink and uplink information within one slot very short in time domain, and they could be corrupted. And of course, when it comes to radio access network, scheduling has a huge impact on air interface latency as well. So mainly by the nature of mechanisms of scheduling, because mainly we can say there is a grant-based scheduling or grant-free-based scheduling. In previous technologies were used grant-based scheduling, which mainly was introduced because of increasing efficient of use resources, increasing the reliability. Whereas in 5G and 4G advanced was introduced grant-free scheduling, and or by in other words we can say semi-persistent type 1 scheduling or pre-scheduling, because it seems to me that this type of scheduling is all the same. And if you know that there is some difference between of them, you can write me in the comment section below. We will talk about it. So grant-free scheduling is aiming for low latency operation, is when a lot of things, a lot of system information is pre-scheduled in advance. If we're talking about more details about grant-free scheduling, it is when G node B could pre-configure next transmissions, including PUSH grants, without any sending scheduling request, without sending buffer status report, and allowing UE to have uplink resources for a certain period of time. So that information may include modulation encoding scheme, frequency and time domain allocations, HRQ parameters. So this is a kind of a pre-scheduling mechanism. Of course, it has positive impact on any latency related testing, in even in small data downloads, but negative impact that very probably uplink interference could be increased, because not so appropriate transmission from UE side is expected in that case. If we're talking about any scheduling mechanisms, we should understand that again, as in previous technologies, the main impact here is when scheduling request sent multiple times, so repetitions. It of course increased delay, and if we have multiple scheduling requests, multiple repetitions of that information, we should investigate. First of all, we should start with uplink interference. Very probably some problems with coverage in uplink, some interference here, and if that could not be mitigated, we could a little bit adjust PUCCH power, but very cautiously, because it could impact on all uplink operations. Also, in case of non-standalone operation, we could optimize switching between two technologies. Also, we could go in downlink direction and check if everything is okay with PDCCH utilization, with PDCH resources. It may have different reasons. One of the reasons for limiting PDCH is interference in PDCH channel, in basically downlink direction. For that reason, we could check if there is a possibility to switch on PDCH beamforming. Maybe it is supported. Also, some PTCH power boost features could be available for that case and could positively impact on a scheduling mechanism. And if previous features is not allowed, we could try to increase overall downlink power as a solution basically for better coverage. Other possible methods is play with B1, A2 threshold, try to optimize to limit coverage. And of course, we should not forget about basic things such as antenna tilts, checking some hardware, software faults. So all of that steps could actually improve scheduling latency. And here is information from one of the IEEE article. They try to evaluate the difference between SR-based and pre-scheduling, between two types of scheduling. And we can see that in 2.1 gigahertz and in C-band TDD, there is a big difference. Almost in 2 times pre-scheduling or grant-free scheduling works better in terms of latency. Also, we should remember that in real network, users are mobile and there are a lot of handovers. In 4G, in 5G handovers, any handovers are hard handovers. So it means system break connection before make new connection. And of course, it leads to some handover interruption time, usually from 50 to 80 milliseconds for 4G, 5G networks. So it means that some time is required for UE to detach from source network, to synchronize in downlink direction with target network, to synchronize in uplink direction with target network. And of course, for signaling, also some time is required. So that's why such handover interruption time is inappropriate for very low latency operation for any URLLC services. And that's why in release 16 was introduced dual active protocol handover solution to reduce handover interruption time almost to 0. Of course, that time could vary a lot. It depends on FDD, TDD patterns. It depends on how exactly UE and what kind of capabilities it has. It may even related to indoor infrastructure if we're talking about indoor cases for underground or any complex indoor buildings. When there is no possibility to plan very good handover overlap area, it may lead to handover drops. It may lead to very long handover execution phase, and of course, this is not a good case for any latency applications. This is an example from 3GPP. They introduced kind of an investigation. Actually, MediaTek company produced that investigation, and then they understood that the main impact on handover interruption time is when UE try to retune RF chain and baseband, especially when it comes to handovers between different frequencies and between different FR ranges. So the main contributor in case of handover between FR1 to FR2 would be that part, would be the part of RF chain retuning. So that's why we should avoid any handovers. It is better when we have very good coverage, we have low number of handovers, because of course it will impact positively on jitter, or we can say reliability of latency. And of course, such solution as dual active protocol handover, it has a lot of limitations. Actually, I have my own video about overall aspects of that solution, but now I'm going to tell just very quickly some of them. For example, that type of handover could increase uplink interference, could have some limitations in terms of power sharing, could have some limitations in terms of UE downgrade in order to perform that handover. But it works, and this is a real solution from 3GPP which could help for low latency operation. Another thing which was introduced in 5G is one additional RRC state. This is RRC inactive state. Actually, RRC inactive state is not so drastically impact on latency, but it has some impact, very good actually, impact on initial connection, initial time for connection. So from that point of view, we should configure and think about how users could be allowed to spend more time in RRC inactive state, because it allows them faster goes to RRC connected state and be ready for packet session. So in overall, we can conclude that there are a lot of solutions which could positively impact on air interface latency. So first of all, we should consider any features which could increase signal to noise ratio. This is beamforming, possible power boost, of course very good coverage planning is also here. Then we should think about how to mitigate interference in uplink and downlink direction, especially in uplink. Also, very good impact could has grant-free scheduling and mini-slot allocation. May use high numerologies, high subcarrier spacing, which shrink slot duration in time demand. Also, when it comes to TDD operation, TDD patterns impact a lot. As one of the possible solution, multi-connectivity handovers also could be used. Of course, we should think about appropriate 5QI settings and mapping between base station and transport network in case of any overload conditions. So there are many things which could help us in order to achieve low latency operations. Now I want to say just a few words between standalone and non-standalone operations and latency. Of course, standalone is much more preferred when it comes to low latency and especially for URLC applications, because it may give us lower control plane latency, it may give us lower uplink, user plane latency, due to some aspects of 5G and R protocols. And of course, only in standalone, we are able to isolate traffic from each other, we are able to implement network slicing, end-to-end network slicing, which is actually designed for implementing low latency communications. Now let's talk about transport and core part latency. So if we look at end-to-end latency budget, we can see that, of course, there is a air interface and radio access interface aspects, and also transport and core part. First of all, in that part, architecture and topology of interfaces and nodes has a huge impact. Then we can say that propagation delay, basically the lengths of optic fibers and any other links, also has impact. Then number of nodes and their processing capabilities. Also, I know that in case of X2XN interfaces, for example, microwave communications could be used, and if they are not configured so well as it required, they also could impact on latency delays. Of course, cost settings and how it mapped between each nodes. And as I said before, any firewalls, any security gateways, and any other inspection nodes could impact on latency. Propagation delay in optic fibers. We know that signal is propagated over the optic line with the speed of 5 microseconds per 1 kilometer. So this is not a speed of light. This is less than speed of light. And also there are some equipment, for example, optical multiplexers, other equipment, they could have some latency introduction, but we may omit it because this is about a few hundred of nanoseconds. This is not a case. Also, such optic lines, they could use forward error corrections, which could also impact on latency about some hundreds of microseconds. And as I said before, some nodes such as switches, routers also may give additional few milliseconds. So what does it mean? It means that in order to meet requirements of 1 millisecond, the requirements of very strict URLC cases, the length of optical path should not exceed 40 kilometers in reality, because we also should consider other delays. What does it mean? It means that mobile edge computing and special radio features, which I just told you before, they are required for very strict URLC requirements. When it comes to transport delay and basically TCP/IP protocols, of course we know that transport link may be not so enough in terms of capacity, and it could impact on round-trip time, especially on the diagram of round-trip time. In the case of limiting capacity of TCP/IP behavior, we should expect some kind of sawtooth of RTT behavior. This is basically the sign of some problems in terms of capacity of links. And in order to calculate congestion-related delay, we may just define the overall end-to-end budget delay, then minus certain propagation delay, which is basically depends on the line, the length of line, and minus other delays. So that's how we can calculate congestion-related delays. Another possible sign of XN/X2 interface actually could be seen from just PRB utilization counters. Like in my example here is when PRB utilization in busy hour do not exceed certain values, for example 80%, and there is a kind of a plateau of PRB utilization. So that could be a very good sign for limiting X2 XN links, and you should check if there is any probable limitations for that. For example, using other counters from OSS networks which were related to that links itself. And now let's talk about how to test latency. Of course, the first method is drive test methods, which is basically aiming for testing air interface latency. I want to list just general advice, which I found very useful, especially in terms of testing low latency applications. So what does it mean? It means that it is better to use UE instead of laptop to initiate any ping commands. It is better to have the UE fully charged and not heating up. Why? Because a high temperature may lead to downgrade of NR features in user equipment. Also, it is very good opinion is when you would try different UE models, because different vendors, chip makers, they could have some limitations. Also, if you use some special, let's say, drive test systems, such as NEMO or Roder-Schwarz or TEMS and others, they could probably have pre-installed special software with specific algorithms to emulate the behavior of certain traffic patterns for mobile gaming, for AR, VR, browsing, for streaming. So if that features is available for your drive testing, it would be really good. You can use it. Also, we can say that static tests are more appropriate than dynamic tests because usually low latency applications, it is more about static user behavior, and basically in static tests, good radio environment are better achieved. Of course, when you perform your test, any other applications, they should be deleted and not be used at the same time. Also, I should mention that some features such as CDRX cycle, they could impact on UE behavior in different RC modes, and it would be very good if you would able to keep UE in RC active mode during the all test. So you should define appropriate algorithms in terms of time to keep UE in RC active mode as much as it possible. When it comes to transport and core part testing, ping measurements could be used for that. And it would be good if you were able to ping different nodes, for example, from base station to Google server, from base station to UPF, from base station to internal application server, or even mobile edge computing server. So different path could be investigated. And if you have some problems with that, it is mandatory to engage cross-functional in order to be able together to understand what is the main contributor. Maybe this is a transport network or end server behavior. And here is kind of a general example of drive test log and ping tests for latency purposes. So the main thing here is to use drive test logs and look at L1, L2, L3 layers and align it with time slot level analysis. So for example, we can configure ping commands with 100 packets, and each of the packet is 500 bytes to, for example, Google server, and then to perform that test in a file, in a text file, and then align that information from the drive test tool. For example, align it with MAC uplink transport block info, with frame number, with slot number, and it may give us more details about how exactly these low layers for air interface work in terms of latency. So for the purpose of calculating different part of air interface latency, we can use L2, L3 event logs from drive test tool and ping test, which was written in timestamps, and we can align these measurements in time domain in order to evaluate each UE delay at each step. For example, we can calculate UE processing delay. If we look at my diagram from the left side, when UE spent some time from application layer to low layer to send information, then there are also some time could be if UE not in RC active mode, and we can look this information here at MAC CDRX event, for example. We can also know that UE send scheduling request and indicate that there is information to send to Gnode B, and also some time is required for UE to wait for scheduling response from Gnode B. Also, as an additional step, UE may send buffer status report to Gnode B to indicate that there are also a lot of ping packets which are waiting for transmission in uplink. And all of that messages we could find in uplink transport block messages. So of course, after that, ping packet goes to Gnode B, goes to core network, and ping response message goes in downlink direction, which is also required sometime for propagation, for downlink processing. And in downlink direction, we can look at MAC PDSCH status report, and again align it with ping tests. So what does it mean? It means that we can calculate every contribution to overall air interface. We can calculate UE processing delay. It can be as a total round trip time minus all previous mentioned steps. What also important here is when when we can define, by doing that, DRX inactivity timer, and it actually should be more than the time which UE spent for propagation delay, for G0B and core processing. So by doing that, we are not allowing UE goes from RC active to RC inactive state, which of course negatively impact on latency. So by doing such alignment, we can understand how exactly air interface in our network works. Also, there is a special protocol which is called TWAMP protocol, which was designed initially for testing purposes. The thing is that we usually use ping tests, yes, but ping test was designed for checking availability of nodes. Ping test is not used for latency measurements, yes, and it not give us the possibility to reflect real data applications behavior. So that's why TWAMP protocol, and basically this is methodology was introduced, and that protocol is based on UDP. We can configure size, frequency, and a lot of other things for that protocol. That protocol actually is supported in multiple nodes, so it is good. And actually, if we look at the structure of that methodology, it means that each sent packet is reflected at the server, at the end server, and a packet of the same size is returned to the client. So it means that we provide equal measurements in uplink and in downlink direction, which is also very important. Here is TWAMP latency testing protocols. You can actually find more about TWAMP in 3GPP document. Very interesting document, strongly recommend to read it. So what the main purpose of that protocol in case of latency testing? The thing is that this protocol allows to emulate of data stream characteristics. So we can test latency, we can test jitter packet loss rate for different models, for e-gaming, for streaming, for any other applications. And that server, which is a reflector, it could be also located closer to base station, so we can emulate mobile edge computing as well. As I said before, that protocol allows us to emulate traffic patterns. So it means it allows us to evaluate the impact of load on latency characteristics. So different models could be created. Like in this example, again from 3GPP specification, here is we can define different phases of e-gaming real-time session. The first phase, it is initializing phase with low bitrate, with low interaction. Then goes sustainable phase with a lot of motions, interactions, loading of new gaming scenes. Then we can see longest sustainable phase with relatively high interactions, and a little bit trailing phase with a fewer players, with a fewer interactions. So by doing that, we can create our own model and test it through our network. Also, it is available to create just a very simple model for estimating end user experience. This is actually my own example. We can use as a kind of a final score, a cumulative metric, which is latency score plus packet data variation score plus packet error rate score and plus any other related to latency KPIs. But every contributor is weighted with certain constant, and these constants depends on a certain application. For example, for streaming, it would be one requirement for constant for weights, and for e-gaming it could be other constants, but overall final score could be as a cumulative metric. For example, Rode Schwarz, they created their own interactivity score. They actually not created, they gave it from 3GPP specification. So we can see that this score is a little bit complex, but every contributor of that score is considered as a probability, and it has their own constants. For example, for real-time gaming, we can see in the table just one parameters. For discrete automation, for industrial Internet of Things, and other parameters. It is created to highlight different importance of latency, of packet data variation, of error rate on overall score. And based on this model, Rode Schwarz created distributions, and actually you can look to their site, look at that paper, which I strongly recommend in order to understand. The main thing which I want to say is it is possible to create pretty complex models for evaluating user experience impact. When it comes to latency requirements for different use cases, 3GPP is also may give us some recommendations. For example, for AR are more required for latency because some visual changes, they not so triggered by motion of the user and by motion of surrounding world. So basically augmented reality are more has more strict requirements for latency. We can see it from that table. Whereas when it comes to just regular gaming with different resolutions, requirements not so strict and could be achieved even with nowadays networks. For VR gaming, very strict requirements for cloud, and for the case of rendering, for cloud rendering gaming is when for our end user we have only a display and any video, and when main video and main video rendering happens at the cloud side. So in this case, in order to satisfy 5 milliseconds latency requirements, very probably mobile edge computing is required. When it comes to VR latency requirements, also such requirements could be found in 3GPP documentations. One of them, for example, give us the estimation radio conditions. But in general, we can see that even for high resolution videos, round trip time is not so critical. More critical data rate or throughput, less interactivity required for VR applications. And at the end of my presentation, I would like to highlight that usually when it comes to security in 5G networks, in any mobile networks, we think about personal data, access to calls, access to identifiers, IMSI, IMEI, SMS data for example, for the purpose of e-banking, or it can be battery drain attacks. But with the But we know that 5G latency can be also considered as one of the vector for attackers, for targets. Moreover, such attacks could be invisible for general users, for any even optimization teams, because we know that on the latency could impact basically everything. And especially when it comes to some time critical services, the increase of latency, even for a little bit, even above certain threshold, could broke the whole service, could broke the all interactivity. So we should tell that with high latency importance, latency could be considered as one of the vector for new attacks. And here is my reference and links for further reading. I strongly recommend to look at Ericsson article at Ericsson site, and also look at Rode Schwarz site and find how exactly they perform different measurements in different 5G networks. Very interesting. They have a lot of articles on that topic, so I'm sure you can find a lot. So basically it was my short video about latency in 5G networks. If you like this video, you can like and subscribe to my channel. If you have any comments or questions, please write it in the section below. Goodbye.